In today's video, we are going to discuss about reduction procedure, which is nothing but reducing the number of nodes in a flow graph. Firstly, we can see that in this video, what is meant by reduction procedure and steps to reduce algorithm and some of examples and everything. Firstly, this is total theoretical subject. I have written like a notes. You can use this in your exam also. A reduction procedure for converting a flow graph whose links are labeled with names into path expressions that denotes the set of all entry and exit paths in the flow graph, which is nothing but for a flow graph we have here entry and here it is exit path. Converting a flow graph with these are called names for a graph. These are called nodes. These are link between 1 to 2. This is path from 1 to 2, which is named as A, labeled with names into a path expression that denotes the set of all entry and exit paths in the flow graph. The procedure is node by node removal algorithm. Steps in reduction algorithm. First, combine all serial links by multiplying their path expressions. Combine their serial links by multiplying their path expression, which is nothing but here we have same example. This is multiplying AB links. Combine all parallel links by adding their path expressions. For parallel links we use sum, like here we have C and D. These expressions can be written as C A B, not B, D. C plus A plus D. The total expression can be written as C plus A plus D into B. Remove all self loops by replacing them with a link of the form X, where X is the path expression of the link in that loop. Here, self loops are nothing but node to itself, like here 1 to 2. This is called self loop to itself. This can be written as X star, where X is the path expression of the link in the loop. Okay, coming to step 4. Here we have select any node for removal other than the initial or final. Replace it with a set of equivalent links whose path expression correspond to all the ways, which is nothing but initial and final node should not be removed firstly. All equivalent loops can be removed. This node can be removed and it should be replaced with equivalent links. This is fourth step. Combine any serial links by multiplying their path expressions. And previously I have told A, B combined. Combine all parallel links with adding their path expressions. Remove all self loops as it in the step 3. Again proceed with step 3. And eighth step is nothing but if graph consisting of a single link between the entry node and the exit node, if we have that, then the path expression for the link is to be same. Here at all, no? This is entry and this is exit. In between we have only one node. It should not be removed, and this is original graph. It should be same. This should not be removed. Step 8 is that we can say that flow graph can have many equivalent path expression between given pair of nodes, which is nothing but many different ways to generate the set of path between the nodes without affecting the content of the set. We can also say that if there is a graph between 1 to 2 and 2 to 3 and 3 to 4 and 4 to 1, this is a flow graph. In these between we can remove 3 flow graph also, 3 node, by replacing it with any equivalent link between 2 to 3 without affecting contents, without affecting the content of the set. And the appearance should expressions depends in general which node should be removed and which link should be placed. It depends upon the appearance of path expressions. Here, cross-term step of 4. Here, whatever written in the algorithm. This is the fundamental step of reduction algorithm. It removes a node, thereby reduction of number of nodes by 1. Reducing number of nodes by 1, and these are successive applications of the step, eventually get you down to one entry to one exit, which is nothing but which have only one entry and one exit. And this is fundamental step in the reduction algorithm, and reducing the number of nodes, as simple as. Here we have one example. This is an here we can take, this is an arbitrary node that has been selected for removal. A, B, C, D and E. Here we don't have one entry and one exit, so and this looks like an incomplete, so we can convert it as an complete by adding this is A, this is B, this is C, and this is D. Now we can convert it as A, C, next A, D, and A, E. Now B, E, and B, D. It can be written, and this is B, C. From these diagram we can create an expression like A plus B into C plus D plus E, because these are parallel lines, into AC plus AD plus AE plus BC plus BD plus BE. Whatever the expression here we got, that is this diagram. We have, from every node we have one path. We get this expression from this, and we convert it into a perfect flow graph, and we got this. Also have like a loop removal. We can take one example for this also. Loop removal, which is nothing but a self loops. Here this can be converting as xz and yz. We can also say the self loop or serial loop. We can see like this. Remove the self loop and then multiplying all outgoing links by z. Here we remove this loop and multiplied with zx and x, y, yz. In the second way, we split the second node into an equivalent nodes, call them as loop removal operations. We can take one example for reduction procedure. First, actually this is not an actual flow graph. Here we have A to B, B to A to 1 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to T. Okay, fine. But here this is an incomplete flow graph. Here we have 7 to 3 and 4 to 8. This is not a correct way of a flow graph. We can reduce these flow graph nodes and convert it into a flow graph expression. The initial step is Step 4 in reduction algorithm, which is cross. Here we have cross stem step 4. We use this step to remove one node, which is nothing but we can remove 10th node by removing this link to 9 and this link from 6 itself. Here we remove 10th. These two links are from 6 itself now. We remove just one node, but the expression is same here. And next we follow the step 4 again, and 5 and 7 2. We can take like removing 7th node and 9th node in between 8. We can remove this node by applying arbitrary node reduction function. 1 minute. Here we can take this. From 6th to directly we are leaving 9th node. We are giving like, I will rewrite this graph once again. 1 2, this is same. But here we remove 10 and we remove 9 now itself, and we have 8 and we should remove this 7. We can remove 7 also. A, B, C and D and E. Here we are passing through I. This is I and this is M. We can take it as I, L, and M also, or else we can also take like I, M, F. We can take and GR links. Here we converted which are going to 3 FJ. We are directly giving from the 8th node to FJ to 3, from 8 to 3 F and J. Here again for 4th node only from 4 to 8 only G is passing, and for 5 it is K, H. These nodes can be reduced to directly K, H. Again for 6th passing I, J and H. So we are directly giving the self loop as I, not J, L, L, I, L, H. And from 3 again we have F, J, M, and here I. So I, M, F. Here already we taken J, so these I, M, F can be converted into one loop. We can also remove 8th node by giving one expression like, here G is passing to 3 only, so we can keep here G, and from these G is also going to 5. G, K, H. This 8th node is removed now. G, K, H. This is not there. Like this we have to keep. Next, same I, L, H, I, M, F. Here now we got G, J, F, G, K, H, I, L, H, and I, M, F. Now parallel nodes can be removed. Here these parallel nodes can be converted by C plus G, K, H, and here one, this should be removed. Next step, then we can also remove 4. For 3 we can give it is like same B, G, J, F by removing the 4. Final diagram will be F into B, C plus G, K, H, D. Here we have I, L, H, D into A. Total we can write is I, H, L, D into I, M, F, B, G, for this self loop. This is nothing but reducing the number of nodes to get an easy exit and entry node. If you need notes regarding this reduction algorithm or reduction procedure, you can ping me.